Ladies and gentlemen, reporting as a please take your seats. Thank you.
Good afternoon, everyone. Hey, did everyone have a fantastic day too here at the Atlantic Festival? There we go. We're so delighted to have you here. We know how precious your time is, and so we really appreciate you spending so much of it with us. We are absolutely thrilled for this evening's program. My name is Patrick Carrigan. I'm Executive Director at AtlanticLIVE, and it is again my pleasure to welcome you all here this afternoon. This evening's exchange, the future of personalized medicine, promises to be quite the conversation. Because of our knowledge of the human genome, advances in medical science can be tailored to an individual's DNA, saving lives and curing once fatal diseases. We've come so far already, and today we'll explore what the future holds. At this point, I'd also love to take a moment to thank Innova for making this evening possible and making the entire festival possible. So a quick round of applause for them. And at this time, it's my pleasure to welcome up to the stage Dr. Stephen Jones. He is the President and CEO of Innova.
Thank you, Patrick. Today's topic is precision medicine and personalized health, and I want to talk to you about my thoughts on that as I contemplated coming together with you this evening. When I was a first-year medical student, I had the opportunity to do a fellowship with the American Cancer Society in the summer, in which I was able to shadow a medical oncologist. And every day we went and saw a patient who had been diagnosed with bladder cancer, and that patient had been diagnosed with a form of bladder cancer that everyone knew realistically the chance that that would ever progress or spread or be fatal was so low that it shouldn't be a concern. But we were seeing him every day because that turned out not to be the case. That he had unresectable metastatic bladder cancer, and that he ultimately was not going to survive. That man was my grandfather. And so the concept of personalized medicine on that individual patient is very real to me as a cancer surgeon. Innova Health System is a system of 5 hospitals and a number of ambulatory centers that's pleased to serve over 2 million patients in the DC suburbs of Northern Virginia. Washington attracted me to this area only 6 months ago from Cleveland Clinic, where I had a very satisfying career as a cancer surgeon, because it's a place where ideas are turned into action. Many people don't understand the role that DC has played in reducing the burden of cancer, from NCI-directed sponsored cancer trials to screening and prevention programs, even all the way back to the Surgeon General's report in 1964, in which we showed that carcinogens, smoking specifically, was a significant issue. At Innova, we're excited to partner with the NIH, the Department of Defense, and others on the Apollo Proteogenomics Moonshot Project. As a key part of that program, our team has performed proteomics analysis on over 8,000 specimens of cancer from cancer patients from this project from around the world. At Innova, we're committed to the war on cancer and proud to be a key part of the Apollo Moonshot Project. But there's more to be done. In my field of urologic oncology, in prostate cancer, we've significantly reduced the likelihood of dying of that disease compared to when I was an intern 25 years ago. But in bladder cancer, the disease my grandfather passed from, we've made very little progress, and personalized health as part of that is going to be a key way that we move that forward. At Innova, we're towards the point of personalized medicine. We think not of cancer, but of your cancer. We're making progress. Immunotherapy, proteogenomic profiling, and targeted therapies can improve survival, and they do. It's now our privilege to hear our speakers, Ed Young, and Francis Collins on the future of personalized medicine. And we want to thank the Atlantic for convening this discussion. It's important to me, important to all of us. Thank you.
Again, our thanks to Dr. Jones, of course, and the entire ANOVA organization. Before we get things underway, just a quick bit of housekeeping. Please, please, please take a quick moment, pick up your phone, and make it quiet. There's nothing worse than having one of these conversations and having a phone go off. So thank you so much for your help with that. But please do not put them away while you still got it in your hand. Make sure that you're participating in the conversation via whatever social platform you're on these days. You can tweet at us using the handle @AtlanticLIVE and using the hashtag #TheAtlanticFest. Again, #TheAtlanticFest. One final note, we'll have time for questions at the end, so start thinking of some fantastic ones for our panelists today. With that, it is my distinct privilege to welcome Francis Collins. He is the director of the National Institutes of Health, and he is here with my colleague, Atlantic staff writer Ed Young.
All right, can everyone hear me? Great, well thank you for, you cannot hear me. Okay, we have someone in the back saying that the crowd noise is, I can't do anything about that, but hopefully my colleagues are on the case. Thank you very much for joining us today. We are here to talk about precision medicine. And now, as a journalist at The Atlantic, I consider myself dispositionally skeptical about pretty much everything. But if anyone can convince me about the worth and value of of precision medicine, it is this man, Dr. Francis Collins. So I wanted to start this by asking you to define for all of us what precision medicine actually means, because the term is used in so many contexts. I wanted to make sure we're all on the same page.
Glad to do that, and wonderful to be here with you and with such a distinguished interviewer. We had a great opportunity a couple months ago where I was doing the interviewing and he was answering the questions.
That's right, it's payback.
Yeah, this is payback time, so be nice. I wasn't that hard on you.
No, that's right.
And certainly this is a topic near and dear to my heart because it is such a promising opportunity to transform the way in which we approach medical challenges. Precision medicine, a term that was particularly put forward by the National Academy about 5 years ago, is the idea of making it possible for, whether we're making a prevention recommendation or a treatment recommendation, to incorporate information about the individual. It's the opposite of one size fits all. Mm-hmm. And most of medicine until now has kind of been one size fits all because that was the best information we have. But wouldn't you rather, if you need a medical intervention, to have it take account of your health behaviors, your lifestyle, your genetics, so that you end up with a recommendation that has the best chance of working for you? That's what precision medicine aims to do. Now let's be clear, we can do that in some instances. An obvious one, if you go to get a new pair of eyeglasses, well, these have been very precisely designed for me, so I can see all of you. I would not be happy with a generic pair. But for many things, how are we going to treat this person's heart disease, or that person's cancer, or this person's diabetes? Until recently, we've been in one-size-fits-all land, and we want to move out of that into something that is more precise and more effective.
And I know that the seeds for this change in medicine were really planted by the sequencing of the human genome about, 15 years ago now. 15. I saw that I found this a news conference from 2000 in which you were quoted as saying, in 15 to 20 years, you will see a complete transformation in therapeutic medicine as a result of this project. So 18 years on now, how do you think we're doing? Has that transformation happened?
Yes, in some places, not yet in others. And we should talk specifically about those examples.
Yes, please.
Certainly in 2000, we really didn't know what the architecture of the genetic contributions to disease were going to look like. We didn't know whether there would be 3 genes that play a role in adult onset diabetes and 4 genes in schizophrenia. I mean, it turned out there's a lot more. The complexity of the genetic contributions to most common diseases is considerable. Mm-hmm. On the other hand, I think what you can point to today that has been transforming is the precision medicine approach to cancer. Cancer is a disease of the genome. It comes about because you have misspellings in that instruction book in a particular cell, and those misspellings cause that cell that was normally well-behaved and knew when to stop growing to keep growing, and sometimes to spread to other parts of the body. And that means if you really want to understand a cancer in a particular person, you want to know what's wrong in that person's cancer, not in sort of an average example. Because your best chance of being able to treat that properly is to know exactly what is gone wrong in that cell. So cancer these days, if I had cancer today, I would want to have that particular tumor analyzed, looking completely at all of its DNA, looking to see which genes are on or off, which genes are rearranged and mutated, and then I'd want to have that information considered as one tried to make a choice in a rather long menu of treatments to pick the one that's most likely to work. That's precision medicine for cancer. That has had some dramatic life-saving examples, including people who already had metastatic disease, but it still doesn't work as often as we wish it did. Maybe 20% of the time now, you get an answer that is highly rewarding to know and results in a better outcome. We ought to be able to do better than that with more information. But it has been transformative, and I think anybody who's in oncology would say we're in a very different place than we were in 2000.
Why only 20%? What would it take to close the rest of that gap?
Well, every cancer certainly has something that's driving the good cells to go bad. You can, with a DNA analysis, identify much of the time what those are. The problem is not all of them are actionable. That is, we don't yet have a targeted therapy for every kind of genetic change that you find in a cancer. We need to expand that menu so that more and more of the time, the result leads you to a choice about therapy. That's the main limitation. The number of drugs that have been developed that target specific cancer changes is growing, but it's not big enough yet. And that's the limitation then in being able to apply this to that other 80%. But that shouldn't be considered as, well, that's it. That's all we're going to be able to do. This will continue to get better.
Sure, so 20% is not a ceiling that we have hit.
Not at all.
And so for those 20%, how well do the targeted therapies actually work? And my understanding was that it is often the case that you get resistance evolving to those drugs, even though they are highly personalized to the patient's own tumor.
And you're absolutely right. And we shouldn't be surprised about that. By the time you have a cancer diagnosis, the number of cancer cells in that tumor is generally in the nature of 1 billion or more. The idea that you could wipe out every one of those cancer cells with a single drug, mathematically, the chances aren't that good that that's going to work, because all it takes is a couple of them to develop resistance, and then the cancer is going to come back. This is very similar to arguments about infectious disease. We don't treat HIV/AIDS with one drug. If you do, you'll get a response, but then it'll come back. Same problem. Resistance arising from mutations in one of those viruses that's no longer responsive. The real successes, if you want to see cures from this kind of targeted therapy, will need to be combinations where you have 2 drugs, and then the chances of a single cell getting resistant to both of them, or maybe 3 drugs, is going to be much reduced. But I have to jump in here and say the other thing that's happening in cancer, which is also very connected to the precision medicine approach, is immunotherapy.
Right.
And I should tell you about experiments that are going on right now in that regard that are very much in the realm of precision medicine.
Please.
Every cancer does have mutations that causes the DNA to produce an RNA and to produce a protein that's not normally there in that person. You are, if you have cancer, you're making new antigens in your body. The immune system is designed to find those, but cancers are very clever. And they have designed their own ways to tell the immune system, there's nothing to see here, just keep moving. The ability to then bring the immune system back into action is something we are learning how to do. The Nobel Prize on Monday in physiology or medicine was for one approach called checkpoint inhibitors to Jim Allison and Tasuku Honjo. That approach, you may have noticed 3 or 4 years ago when Jimmy Carter announced that he had metastatic melanoma to his brain, and we all thought, well, that's not going to go well. Jimmy's doing great, by the way. He got one of these checkpoint inhibitors, and it worked. But it doesn't always work either. So there's a precision medicine question here. Which kind of immunotherapy is going to work for which cancer in which person? Something that we're now sorting through. Many of us think, ultimately, that a combination of a targeted drug therapy and an immune therapy might be the most powerful way to go. But coming up with ways to test all of those many combinations is not something you do overnight.
Mm-hmm. It seems like this is one of the running themes of a lot of biomedical research, that we think it's a certain way and our biology proves to be much more complex than we previously thought, so we need to recalibrate our model for what we can actually hope for in the future.
Indeed, as we often say at the end of a news release, more research is needed. And it's always true, and that's why NIH needs to be funded generously, I might say. Just
in another 5 years. Nice, very smooth.
Thank you for the applause.
Okay, so we've talked a lot about cancer.
Yeah.
Tell us about more other settings,
Sure.
other medical conditions
Right.
for which this is.
Let me tell you another one that's pretty dramatic, and that is the evaluation and ability to come up with treatment for children that are born with mysterious conditions that in the past we couldn't figure out. And it happens much more often than you might think. Roughly 2 or 3% of children are born with some kind of a birth defect. Many of those, the majority of them, are genetic. A vast fraction of the time in the past, you just didn't know what the cause was. Maybe you could try to scan through previous reports and see if the particular collection of abnormalities fit with a particular syndrome that somebody had described, but it was pretty unsatisfying. And you rarely knew enough about what the mechanism was to come up with a treatment. Mm-hmm. That has all changed. And now, if you have a circumstance of that sort, it is almost becoming the standard of care to do a complete genome sequence and see if you can identify what the mistake is. And a fraction of the time, I wish it was a much higher fraction, but a significant fraction of the time, that not just gives you a diagnosis, it gives you a therapy that is actually appropriate, targeted for that purpose. Last night, there was an award ceremony for the federal employees that work for the government. The Federal Employee of the Year was a physician scientist at NIH who has used this approach to identify the cause and the treatment for a whole new class of inherited conditions. And some of his patients were there, and they are absolutely cured because of the ability to identify the cause and then come up with a treatment.
Which condition?
This is a group called autoinflammatory disorders, where your body reacts as if there was an inflammation of some sort that they needed to respond to, but there is no infection, there's no reason for it. And ultimately, it's life-threatening because you get fevers and ultimately you wreck your kidneys and your liver. And Dan figured out the genetic causes and was able to identify then that we do have drugs already that were developed for other things that turn out to be great for this. None of that would be possible without precision medicine. We would basically say, we don't know what's going on with these individuals who have these bouts of fever, and ultimately we know they're not going to do well and there's nothing we can do. That's all changed. And for all those kids with birth defects that we used not to be able to identify, this is a big deal. Another area that is coming, but it is still not there, is the ability to identify for an individual who needs a therapeutic intervention. Is this the right drug for that person? Is it the right dose for that person? Is it the right time to give that drug? There are progress areas to report. If you need a blood thinner because you have a problem with blood clots, particularly in with atrial fibrillation or with deep vein thromboses, the common drug that's given, warfarin or Coumadin, is one of those that has a very narrow zone between not enough and too much. And yet that is determined by a couple of genes that are commonly variant. With that information, you can reduce the likelihood of somebody having a bad outcome. So this is called pharmacogenomics, drug decisions based on genomics. There are more than 100 drugs that the FDA label says you probably want to know the genetic variant in order to get the dose right. For the most part, we're not using that information because it's not been sort of integrated into medical practice. But that is coming, and that will be a significant precision medicine advance that everybody will begin to notice when they need a prescription. I'd love to see more of that done for antidepressants. We know how difficult it can be when people are afflicted with a serious depression, and oftentimes you have to try 3 different antidepressants before you get one that works. That ought to be something we could do much more precisely when we understood the information.
To what extent do we have the knowledge to do that, and to what extent is it actually applied in clinical practice?
Great question. We are still short of the depth of knowledge we need, although we have quite a lot. I think we have enough that we could start applying this broadly in medical practice for such things as blood thinners. For antidepressants, still in the research phase, but more and more evidence gathering to say we ought to be able to move that into clinical practice in another 3 or 4 years.
Okay. So these examples sound great. Like, are there like counterexamples that keep you up at night, where the approach hasn't worked as well as scientists would have hoped for?
I had hoped, and I think I probably talked about it in 2000 if I go back and read that script, that we would come up with a circumstance where we could do a better job of individualizing prevention based on your inheritance. I wonder how many people in the room have had a DNA analysis by a company like 23andMe or one of the others. Let me see hands.
That's
a lot of people
yeah, it's a few dozen. Okay.
have been acquiring that information. I've done that as well. When I had mine done 10 years ago, it did allow predictions of risks for common diseases, things like diabetes and cancer. And I had to notice when I sent my DNA to 3 different companies that they gave me 3 different answers, which, I mean, they got the lab part right. They could do the DNA analysis and say, yeah, you have a G there instead of a T.
It's so precise, it realized that you're 3 separate people.
I did not use my own name. I thought that might be a tip-off to them to look very closely, but...
So Dr. Colin Francis.
I'm not saying that. But it was clear that the interpretation was very much all over the place because the field of figuring out how those variants play out in an individual was still early. Well, 10 years later, it's better, but it's still not quite to the point where I had hoped it would be. I will say, what I think we'd like to see is a circumstance where you had really valid information from that kind of genetic analysis that would be as good as a cholesterol in terms of telling you, okay, you're at higher risk for heart disease, or you're at lower risk for cancer, something that is statistically as significant as the kind of biomarkers we use as measuring your blood pressure or measuring your cholesterol. We are getting quite close to that. In fact, a scientist named Sek Katharison in Boston has just published a paper that claims we are there for the kind of measures of risks for diabetes and heart disease that are as good as what we have with other kinds of biochemical measures. So maybe it's about time to move in that direction.
And that gives you a sense of your personal risk, but how do you then bridge the gap between that and personalizing, say, preventative measures? Is it all just going to come down to, well, okay, so you should eat healthily and exercise more and all the rest? Do you see a future where the actual advice that people get is more granular than that?
It should get there. I will tell you, when I had my analysis done 10 years ago, all 3 of the advisors agreed that my risk of diabetes was about twice the average person. I found that particularly distressing because some of the factors that they tested had been discovered in my own lab. It was like, really? But it got my attention, and I was 30 pounds heavier then, and I had no visible exercise plan, and that was a wake-up call. And for the last 10 years, I've had a very vigorous exercise plan. I lost the 30 pounds and kept them off. Now, that's a motivator. I should have done that anyway, of course, but it is an example of the way in which individual information could be one to cause people to think a bit more about their own health maintenance and whether they're focusing on the right things. Because right now, You get told what you're supposed to do with diet and exercise and don't smoke and all the other things, don't gain any weight and all of those things. And it rolls off a lot of people like, well, of course, they say that to everybody, but I can point to all those people with bad health behaviors who live to be 95. Winston Churchill comes up rather quickly in those conversations. It would help a lot more if somebody said, well, your particular risks are these 3 things, and these 3 things over here, you're actually at lower risk, so maybe those are less important for you to pay attention. Individualizing is going to be more motivating. We already have data to show that. So we're on the way to that, but we're not there yet. This is going to bring me to make a pitch for what we need to get there.
All right, go.
You know I'm going there, don't you, Ed? What do we need? If my dream here about both prevention and treatment of chronic disease is going to come true, we need data. We need data on a lot of people. Data on people who have agreed to be our partners in research, to make their medical experiences part of a long-term study. People who are happy to have their complete genomes sequenced. People who are willing to have all kinds of lab tests, fill out all kinds of questionnaires, walk around with wearable sensors like Apple Watches and Fitbits, and have that information also part of the record that researchers can use to dig through and say, okay, for this person, here's what happened. Maybe we could figure out an implication for the next person from that. And it has to be a really, really big study for that to happen because we're all different. How about 1 million? Does that sound good? Well, that's the study we're doing. That's the study called All of Us. That's the study that was launched on May the 6th with a launch in 7 different parts of the country and is enrolling already. We've reached 115,000 people who have started the process of signing up, and half of those are fully enrolled already. You can sign up, joinallofus.org, joinallofus, one word, .org. And the idea here is to have, for the first time, that kind of incredibly comprehensive database from which you can derive inferences about how to keep people healthy, because a lot of these people are going to be healthy, and also how to keep people from getting sick and what to do when they do have that experience. It'll be unlike any platform for information we've ever tried to construct. You've heard of Framingham, the study that has figured out a lot about heart disease. Well, that was about 25,000 people and pretty much focused on one area, cardiovascular disease. This is 40 times bigger, and it is all diseases, and it's the kind of data that Framingham never had access to because we didn't have the technologies we do now. So this is transformative. It will fill in so many of the gaps that you're asking me about how are we going to get from where we are to where we want to be.
I'm going to ask you about it in 15 years. We'll see how we do.
You're on.
Okay, but so I know that a part of the this All of Us initiative is specifically geared towards getting more participation in genetic research from groups that who are not of European descent and who have not been a part of the genetic revolution so far. But I want to ask you about the tension there, because on the one hand, yes, it is absolutely great for people from these communities to finally be included in genetic research. But I can also see why people from marginalized groups might be skeptical or wary about what happens when they hand their genetic data over to someone else, and whether the flip side of precision medicine could be precision discrimination.
So I'm glad you brought this up. This is a signature part of this project, which is to focus on health disparities, and you can't do that unless you have large numbers of people from underrepresented groups. Of that 115,000 that have already started to sign up, 49% of them come from underrepresented groups, that being African Americans, Latinos, Native Americans, and that's the largest representation of that kind of diversity in any study that we've ever tried to do. And
At the NIH? Or the
that the
US?
NIH has tried to do.
Right.
And this is, again, collected from all over the country. We are also focusing on people in socioeconomic stress by inviting people in community health centers to take part. And they have also been delighted, in most instances, to be asked. They haven't all said yes, but it's like, oh, you're interested in us. We need to be included. Okay, let's think about that. And also rural communities, which tend not to get much attention in many medical research studies. So diversity in every sense is our goal. Actually, in the beta test that we did for this, very carefully trying to figure out what's the receptivity of people who are approached about this, About half of the people that we asked said, yes, I want to take part, and have decided to take part. And that was true, regardless of which group we were asking. As long as it was clearly explained, what is this project? What's it about? What kind of information am I going to get back about myself? People want to know. If you know something about me, I want to know that too. If you've determined my DNA sequence, I want that too. We're going to give it to them. This is pretty unprecedented in terms of the openness of sharing of all the information. That's carried a long way. And we've worked really hard working with communities, trying to figure out how to do this in a fashion that this is not Big Brother coming and saying, I want all your data. These are your friends and neighbors who are part of this effort, trying to do something together here. When we launched this on May the 6th, I went to the launch in New York, and it wasn't in the places where the rich people live. It was in Harlem. And we had a phenomenal day at the Abyssinian Baptist Church with conversations about this and reflections on the fact that medical research in African Americans has a very difficult history with Tuskegee and all the other things that have happened since then. And the conclusion of the leaders in that community were, this time we want to be included, but you better listen to us about what that means.
And what does that mean?
With that, that they want information back on themselves, that they want your database to be absolutely the most secure database that's ever been designed, that nobody is going to figure out that I'm Edna Jones and that's my stuff. They're going to know that there's somebody in the database who had these medical issues, but not the individual identifiers. And we have promised them, to the extent that it's possible these days with data security, that we're going to do everything in that form with end-to-end encryption and every other kind of test of our system to be sure it's not hackable.
Okay. I'm going to throw it to questions in a little bit, but I'm just so think about what you want to ask. But I just want to ask one more, and this is going to go a little off-piste, but it is on the topic of diversity, which we've been talking about. Given the current political moment, I feel I would be remiss if I didn't ask about this. But I know that the country is very much thinking about issues of sexual harassment right now, and this is a problem within the sciences.
Yes.
And I know that you have faced pressure from scientists and some members of Congress about whether the NIH is taking hard enough steps to deal with people who have received your funding and who have been found guilty of sexual misconduct. Do you think that you are doing enough? Could you be doing more?
I really appreciate your raising this because this is on all of our minds right now, and certainly that includes me. This is a critical issue that's been neglected for too long in the scientific community. This kind of sexual harassment has been going on for much too long and oftentimes underreported and not responded to. What we can do at NIH certainly relates to our own employees, all 23,000 of them. We have implemented in the course of the last few months a much more rigorous system where sexual harassment complaints can be handled in the most objective way with a rapid response and not blaming the victim. And that is going to be quite transformative, I think, for the atmosphere that you will find out in Bethesda in our intramural program. But of course, most of our money goes out to institutions all over the country, as you know, our grantees, all those universities and institutes that do the work. We have a challenge there that keeps me from being able to do as much as I would like to, because our grants go to the institution, not to the individual. Mm-hmm. The institutions, for their part, as a condition of the award, are required to say they are adhering to all the requirements of Title IX, and that they have an institutional official who will handle any concerns about sexual harassment. We do require them to tell us if somebody is put on administrative leave because of a concern about harassment, and we are then in that position of shutting down that grant or finding another investigator to lead it. Mm-hmm. But for legal constraints, which I now know a lot more than I ever thought I would need to, and they relate to things like the Richardson Rule. Sometime I'll tell you about that. We are not in a circumstance where we can directly demand that our institutions have to tell us every instance where sexual harassment finding has happened. I think it would be much better if we had that authority. Mm-hmm. We are seeking ways to get it.
Okay. Thank you very much. Francis Collins, ladies and gentlemen. All right, so we have roughly about 10 minutes for questions. You all look like an amazing audience, so you definitely don't need me to tell you this, but I'm going to anyway. The 2 rules for this Q&A session are please ask questions instead of offering comments, and please limit yourself to 1 question per person. There is a roving mic that's going around, so there's a person in the back.
I can project. Can you hear me from here?
I can hear you, and I can summarize your question too.
In determining, precision medicine outcomes and determining results of those studies.
Okay, so this was a question about how AI influences precision medicine.
A wonderful question, and one which we at NIH are deeply interested in expanding the research in that space. Artificial intelligence, machine learning, deep learning, all areas that have found applications in biomedical research, oftentimes in evaluating images, which turns out computers are better than radiologists in a lot of cases, which radiologists don't like to hear, but it seems to be true. But what about genomics, precision medicine? Already that's being attempted in cancer. You may have heard about IBM Watson being brought to the fore, trying to see if they could do a better job in figuring out what's the right treatment. I would say early days for that, but the potential here is enormous. We will be, in the course of the next year, I think, significantly expanding NIH's investments in artificial intelligence research across many different areas, but precision medicine will certainly be one of them.
Hi. Yes, you. Hello.
You're going to hold it. Okay. Thank you for this. It's been fascinating. Can you talk a little bit about how we're doing in dementia and Alzheimer's and the cognitive conditions that alarm a lot of us at a certain age?
Yeah, well, we should all be alarmed when you see the way in which this particular disorder is causing such tragedies in families, and not to mention the economic stress on our country, which is now approaching $300 billion a year and headed for $1 trillion. We do know a lot more about Alzheimer's disease than we did 10 years ago. We certainly know that this is a condition that has genetic contributors, and particularly one called ApoE. But we now know of dozens of places in the genome where small changes contribute to a heightened risk, which means it's possible to identify people at high risk before they have any signs of cognitive decline. One of the things we've learned about therapeutics is you don't want to wait to try that new therapy until somebody already has significant symptoms of Alzheimer's, because by then they may have lost more than half of the neurons in the brain, and those are not probably going to come back. So the whole shift has been towards intervening as early as possible. For instance, people who have that ApoE4 risk factor, especially if they have 2 copies of it, are volunteering to take part in a clinical trial to remove that amyloid protein with a monoclonal antibody, even though they have no symptoms at all. And certainly people who have the amyloid you can see on a scan are also volunteering to do that, even though they have no symptoms at all. That's the direction everything's going. But on top of that, I think we are learning through a lot of this systems biology, proteomics, transcriptomics, all these omics things, that there are a lot of other things in Alzheimer's disease that go beyond what we knew about the 2 favorite topics, amyloid and tau. There's a lot of other potential drug targets that haven't been perceived previously and now can be pursued aggressively and are being so. I co-chair an effort with industry to try to bring academic researchers and pharmaceutical companies working on Alzheimer's together so that we can learn as fast as we can how to get to that next generation of treatments.
So more research is needed.
More research is needed, a lot more.
Hi, yes, you, hello.
Show the effect of some of the treatments, how does that roll out to clinics in the communities and out in the rural areas? Thank you.
Yeah, another great question, and one that unfortunately in this country we don't have a great track record, because at least 10 years ago when somebody looked, how long does it take between the time you have evidence that a particular medical intervention is going to provide benefit and when it becomes part of the standard of care? It was about 20 years. That is unacceptable. We don't have time to wait for that. So how do we do that implementation? A lot of it comes down to, is it going to be reimbursed? Because if it's not being paid for by a third party, it's going to be pretty hard for this to actually become standard of care. I've recently set up a leadership council between NIH and CMS. Seema Verma and I co-lead this effort to talk about exactly this question. How can we shorten the time between when maybe an NIH study says this is in fact evidence that a particular intervention is going to work, and working with FDA and CMS, it becomes the standard of care, and Medicare and Medicaid start to cover it, which means third parties start to pay attention as well. I will say, coming back to all of us, one of the things I think we could do in this project is to shorten that timetable, because a lot of the individuals who are volunteering for this are part of health provider organizations, and the health provider organizations are excited about taking part. So as information comes out of all of us that's actionable, those health provider organizations, big organizations with millions of patients, are going to raise their hand and say, we're using this now, come to us. They'll use this as, I think, an opportunity to recruit other participants in their plans because they're on the leading edge. At least that's my hope and expectation.
You back?
Yes, what's the future of precision medicine for the diagnosis and treatment of Parkinson, particularly early onset?
So the question was about the relevance of precision medicine to the treatment of Parkinson's, particularly early onset.
Yeah, another great question. When I was in medical school, I asked the genetic expert, because I was interested in genetics already, can you name any diseases for which genetics have no role? And he said, well, sure, everybody knows Parkinson's disease has no genetic contribution at all. Well, boy, was that wrong. We now know a lot about the genetics and the biochemistry, and there's a protein called alpha-synuclein that deposits in particular parts of the brain that causes those neurons to get in trouble. We are rapidly beginning to understand that Parkinson's is not one disease. It's probably at least 3 or 4 diseases, and the interventions are not going to be the same for each of those. So this is getting into that precision medicine space. We also are understanding what some of the druggable pathways might be based on really good neuroscience. Again, just this year, back in January, started a partnership with industry to try to accelerate the process of moving Parkinson's into this precision medicine space. It's looking promising, but again, I got to say, of all the diseases that we're trying to tackle, the ones affecting the brain, they're going to be the hardest. The brain is this incredibly complicated space. You have 86 billion neurons there between your brain, between your ears, and figuring out how those circuits work, which we're trying to do in a basic science way, and what to do when things go wrong. This is really hard.
Am I right in thinking that for Parkinson's and for Alzheimer's, which has been asked about, these have been challenging to apply this tenet towards so far?
Challenging. And I think we've learned a lot about risk factors and who's at risk, but translating that into interventions that are going to work, that's hard.
Biology is complicated, right?
It is, and especially with diseases where you don't actually show symptoms until a lot of damage has already been done. All this means that we have to identify the high-risk situation and intervene while people are still apparently healthy.
Okay. Lady in there. Hi. Yes.
At what point do you think that genetic testing will become common in everyday providers like Blue Cross Blue Shield, Kaiser?
I don't know the exact moment. It's obviously going to happen variably depending on the health provider and the diagnosis. I would say, and I said earlier, for cancer, I think genetic testing of the cancer is almost becoming the standard of care now. When will we get to the point where all of us will have our complete genome sequence determined and placed in our medical record so the information is there to act upon? I had sort of hoped we'd be starting into that space now because it would be useful. The costs have been a bit prohibitive, but I got to tell you, that should no longer be much of the reason. Pretty dramatic, I got to say this. The first human genome took us 13 years, cost $3 billion, got that done 15 years ago. You could now get your genome sequenced at a much higher accuracy than we had back then in 2 days for $800. I don't know any technology ever that has had that kind of trajectory of speed and reduced cost in such a short period of time.
I think we're out of time, unfortunately, so I'm really sorry for anyone who hasn't been able to ask a question. Really like to thank Francis Collins for joining us. If anyone wants... If you want to know more about these topics, you can find good reporting at theatlantic.com. My colleague Sarah Zhang is one of the premier genetics reporters in the country. You can check out her work on our website, and the rest of us cover this topic too. Thank you very much for joining us.
Thank you.
Thank you.
Thank you very much. And that does it for this afternoon's program. Thank you all for being here. And again, thank you again to Dr. Jones and the fine folks at ANOVA for making this evening possible. Just a quick update for some of the things you can look forward to at the remainder of the festival that you'll definitely want to be here. We've got a lot more tomorrow. Our main stage program starts promptly at 9 a.m. tomorrow, where we'll be joined by Supreme Court Justice Stephen Breyer. So that's going to be pretty fantastic. You're not going to want to miss that. Thank you all so much, and have a fantastic evening.